So the example we will look at will be specifically will be counting triangles. So we have the set Gn will consist of all graphs of size n, simple graphs of size n. You can model them as a long binary vector with zeros or ones, zeros when you don't have an edge and one when you have an edge. And the length of the vector will be n choose 2, which is a number of edges you can form in between n vertices. And in this graph, on this function, you can count the number of triangles that you find in a graph, that is I connected to j, connected to k, connected back to I. And you can also count the number of edges in the graph. And they are typically going to be proportional to each other. That is, you increase the number of edges, you typically increase the number of triangles, but you may want to maximize, for example, number of triangles given a fixed number of edges. The number of triangles and also the number of edges are a special case of what is called subgraph count. You fix a particular pattern. In this case, the pattern that I was fixing is a complete graph on 3 vertices, K3, and complete graph of 2 vertices. Complete graph on 2 vertices is just one edge. Complete graph on 3 vertices is a triangle. And I count the number of those and the number of those. And you can also write these in terms of the adjacency matrix of the graph. Every graph is connected with an adjacency matrix. You put a 1 whenever you have an edge, and 0 otherwise. You have an n by n matrix, symmetric matrix. And you can write, for example, number of triangles by going over all triplets ijk and multiplying aij by ajk by aik. You will get 1 only if all 3 edges are present, and that will count the number of triangles. So in extreme combinatorics, you might want, for example, as I mentioned, to maximize the number of triangles over the set of all graphs, given a constraint on the number of edges. Of course, if you don't put the constraint on the number of edges, you just end up with a complete graph, and that's not a very exciting or complicated problem to solve. In contrast with the extreme combinatorics, you also have in elementary probability, you have the typical behavior of graphs. For this, you need to put an ensemble, random distribution on graph, and the most classical and typical random distribution people use is the Erdos-Renyi random graph, where you have a set of vertices n. Every edge appears independently with probability p. In that case, because you have a lot of independence, all these functionals are going to concentrate very well around their means. You will have very nice concentration of measures, and the means are very easy to calculate. So for example, you can calculate the mean number of triangles, the mean number of edges. You have n choose 2 edges, and you multiply by p. You call it m. This is a constraint. The expected number of triangles, you have n choose 3 choices for ijk, and then you multiply by p cubed, which is the probability of getting all 3 terms in this product equal to 1. And because the number of triangles and the number of edges are going to be concentrated, you can extract p out of the first equality, plug in the second equality, and you will get the growth of the number of triangles per number of edges in a typical graph of this model. There is a way to go in between, and the way to go in between involves large deviations. Large deviations is a way to go in between. It's a soft way of doing extremizing. You are looking at, a typical graph, but you are asking how the graph looks under the constraint. This I will call capital T, script T, K3 of delta. The constraint is the number of triangles in the graph is going to exceed the typical value. So instead of being n choose 3 times p cubed, it's going to be n choose 3 times q cubed, where q is slightly larger than p. And this event tends to increase the number of triangles, but it makes a graph quite unlikely. So it's getting closer to the behavior of the extreme graph. And usually to understand the conditional law of the graph given the rare event, you start by understanding the asymptotic of the probability of the rare event. You try to achieve the rare event, as Alan Sol explained in his talk. It's very similar here too. You have a hunch what should be the way to get the rare event. You calculate the probability of your hunch. If the probability of the rare event it matches the probability of the hunch, you have a good belief that the hunch is actually the most likely way to get the rare event. And this may suggest what will be the structure of the graph conditional on the rare event. And that's the way we will go about dealing with these problems. So again, let me repeat. We have the setting. We have an Erdos-Renyi random graph on n vertices. I will denote throughout the lecture the law of the graph by mu n p of g. These are the two parameters I play with, the size of the graph and the probability of every edge. And then we have, in general, triangle counts. Well, later on, we will count some other more general subgraphs. We have the expected number of triangles, and we are interested in conditional on the extra triangles, that is on the event of having more triangles than usually. How are the edges distributed? So now we are in the business of trying to figure out what is a good hunch to make to good guess for the behavior. And there are a few possibilities you might think of. One, the most natural one to imagine, is simply change the P to Q. You see, this is even my parametrization is suggesting this. Just change P to Q, and this will become typical in an Erdos-Renyi graph with a slightly bigger edge probability. But there are ways to get extra triangles by a smaller mechanism. There are ways to get extra triangles by a smaller mechanism, and two ways are indicated here in blue and red, and I will keep blue and red and green for these strategies as we go along. So the blue strategy is to add a clique. A clique is a complete graph of a somewhat smaller size. Once you have a complete graph of a size L, you get yourself freely L choose 3 triangles. You can play with L to do the job, and this is one way to get an extra triangle, kind of guarantee, not trusting anything random around. A mixed procedure is a planted hub procedure. In the planted hub procedure, what you do, you take an even smaller collection of vertices, and you just connect them to everyone. When you connect them to everyone, you create a lot of these edges for free, and now there are chances at random for other people to connect and get the other wedge. For a triangle, you need one edge and one wedge. So you get yourself the edge for free, and then you trust randomness to give you the extra piece. So these are at least 3, and you can start thinking of more complicated things, but I will stop at this point. And for dense graph, this story was checked. This story was checked and done in 2 papers by Chatterjee and Varadhan, and then follow-up work by Lubetsky and Zhao. I will return to these 2 papers later on. And what Chatterjee and Varadhan did, they derived a large deviation principle for this situation, and they found that the strategy A, just changing changing the density uniformly, is the winning strategy in a large part of the space. This is indicating P versus Q. Here, Q is bigger than P. This is my parametrization. And Chatterjee and Varadhan proved that find a sufficient condition for the green strategy. And here is a sufficient condition for the green strategy. What they did, they derived a large deviation principle, moved the problem from a probability problem to a variational problem, and found a domain where the variational problem is satisfied by a constant, by this changing P to Q. And Lubetsky and Zhao did an analysis work. They just took the variational problem that Chatterjee and Varadhan found, and they actually characterized exactly the domain where green is, the most necessary and sufficient conditions, and that is the biggest area where you can get the green. The question mark is the area which is definitely not green, and up till now, nobody knows what it is. It is probably neither blue nor red. It's something more complicated, and there is no understanding what it is. We will move to a similar situation, but in the sparse graph case. Sparse graph correspond to the situation where as n increases, you let P go down to 0 at the same time. And the reason is, if you think about it, in a dense graph like this one, the degree grows with the size of the graph. If you are trying to model, for example, a social network, internet, many such things, even when the graph grows, the number of people connected to a particular individual is not growing, definitely doesn't grow linearly with the size of the graph. So it's not a very good model for certain situations, applications. So with the Shurov-Chatterjee, we looked at the problem of how to extend this work of Chatterjee and Varadhan, how to derive something similar in the sparse case. And this motivated a more general study of large deviations for general functions, Boolean functions of large number of parameters. So think of D as large. In our example, D will be n choose 2, but in general, it's a number that goes to infinity. So you have a function f, a complicated function of a binary vector, and you are interested in finding the tails of this function. And the way we do it, we are going to study instead Gibbs measures. So Gibbs measures are measures whose density, here it's discrete, so the density is just a probability mass. The probability mass is proportional to e to the h for some Hamiltonian h. And the idea is that you will take, for e to the h, you will take a smooth approximation of the indicator function. And then the probability under some measure, nice measure mu star of f exceeding L is given by the partition function for your Gibbs function. If e to the h is really an indicator, if you plug it here, you see that this sum is nothing but the probability of this set. And the advantage of the smooth approximation is that you can use Taylor's, you can differentiate, you can do all sorts of approximations which are difficult to do on indicators. So this is just an approximation of an indicator, as I mentioned, by e to the h, and then you sum up. Now, what is useful here is that for a partition function, for a formula of this type, we have in large deviation always a dual parameterization. The log of z, the log of this sum, can be written as a supremum over all probability measures of the linear functional h times the candidate probability measure nu minus the relative entropy between nu and your known distribution mu star. Now, this equality is very sometimes useful, but in this case, it's actually useless because if it is complicated, the reason it is complicated to find z or to find this object is simply because the space is discrete and very large. The space of measures, probability measure over a discrete large set is not more nice or easier. However, sometimes what you have is you have good reasons to believe that naive mean field approximation will work. Naive mean field approximation correspond to the statement that this supremum is actually achieved approximately by product measures. Now, product measures are much nicer because a product measure on a space of D binary variable is characterized by its marginals. There are only D of them, and you need one number for each. So it's just D numbers. So it's not a very complicated object. And if your measure mu star, the basic measure, like in our case of the Erdos-Renyi model, is actually a product measure itself, then the relative entropy breaks down to the sum of the relative entropies of the marginal, and this variational problem is actually quite doable. You actually can solve it usually relatively nicely and find the optimizer, unlike the original variational problem. Now, the reason this is called naive mean field approximation is coming from physics, because it usually doesn't work in real problems of interest to physicists. It usually doesn't work, for example, in low temperature spin glass or disordered models. Then it's hopeless to do such a procedure. But in problems where, like ours, where everything tries to be at the same direction, there is a good hope that this will work. And in this paper with Chatterjee, we found conditions on the gradient of f. We said if you have a function f and you calculate its gradient on the hypercube, and the gradient doesn't take too many different values, or if you want alternative, you can approximate it by not too many values, then this wiggle thing actually is valid, and you can use it together with the first step in order to approximate the tail of such functions. And specifically, our goal was to do it for the case of sparse random graphs. Now, this approach has been extended and refined in a series of works. Jan extended it from binary to a general alphabet. Ron and Eldan made much better conditions and more elegant result by employing stochastic analysis and Gaussian processes in order to write better sufficient conditions. These were improved and sharpened by O'Geary, and also Austin used information inequalities to understand better the conditional behavior of the solution of this, what is a maximizer of this variational problem. And, but the disadvantage of this approach in our context, and in general in any other context, is actually lying in the first step. This approximation by a smooth function is very good as a general tool. It gives you some leeway, but it will never allow you to recover the optimal result in this case. So in particular, when you apply the whole scheme to the context I was talking about of looking at subgraph counts for Erdos-Renyi graphs, you will stay far away. The P, the probability P will not allow you to take the probability P as low as you can get or you believe that you can get. You will get stuck far before the optimal. And that's because of this approximation that you will never recover afterwards. It looks benign, but it's actually cost you a lot at the end. Okay, so motivated by this naive mean field approximation and the Gibbs measure, I want to introduce the family of exponential random graph models. This is something that is used in practice as a way to design graphs with nice models on graphs which have a more interesting structures than Erdos-Renyi graph. And the way it's done is as follows. You take some patterns, think of L being, for a moment, being just one pattern, and think of F as being the triangle. So what you do, you modulate your basic vanilla, if you want, independent edges Erdos-Renyi graph by putting an exponential weight function which emphasize the number of counts that you get of these functionals. For example, the number of triangles. So what you do, you may be multiplying the measure of every graph by e to some power, some constant times the number of triangles you find in these graphs. In order to make this manageable, or to figure out what this correct scaling is done, typically what you do, you take the number and you divide it by the expected number, just to scale things correctly. This will make it so that this nominal count is now centered around 1. And I will keep using T of F of G as counting the number of patterns of subgraph F in a big graph G, but normalized by the expectation under the Erdos-Renyi graph. So you always get the vanilla version is 1. And then you multiply it by, take some function of it, maybe, or just put it in the exponent, and multiply by a large constant R. Now, the constant R is going to be determined by the large deviations of this measure mu, because if R is too small, you will just get back the Erdos-Renyi. It will have no impact. If R is too big, this will dominate and you will not see anything of the original structure. But if you know the tails of mu and G, then mu and P, then you can calculate what R to put in there. We are going to look at the ferromagnetic case, meaning the parameter beta here is positive and the function that we use is monotone increasing. So we are trying to promote the appearance of more of these patterns. It's a very different story if you try to eliminate those patterns. So we are not going to get there. And you also have a normalizing number, the partition function, just to make the probability measure mu and P beta into a probability measure. So this Z is simply the sum of these weights over all the configurations. Now, it is known in large deviation, this is Varadan's large deviation lemma, that if you know what is the probability of the upper tail, what is the probability that the ingredients of this Hamiltonian are going to exceed the nominal number 1 by delta K, if you know the log of these probabilities, how it decays, and it scales like R, so the log of this probability is like E is like minus R times this function, which is explicit order 1 function, then you can calculate the partition function, and it's going to be given by an optimization problem where you go over all the possible values of the deviations, and then you take the cost of the deviations, the E to the minus J, and in return, you get a gain from the amount that you get in the Hamiltonian in your weight. And you just take the supermum over all the possible parameters. And here the parameters you will take are only no negative because you have an increase only if you make the things bigger, right? Because all my functions here are monotone, there is no benefit for me to try to get any functional less present than it should be. Now, from this, you also conclude It's not exactly a mathematical theorem, but a folklore, that if you want to understand how a typical sample from this exponential random graph model behaves, what you need to know how the Erdos-Renyi graph behave conditional upon the rare event. Here, it's a small probability event, but this is actually, if you choose a delta that makes this a maximum, it will be the typical behavior. So the point is that when you move to this new ensemble, what was rare originally is now becoming typical. So if you want to understand these graphs, you suddenly need large deviations on the original one to understand the typical behavior in the new ones. So this motivates us to look at large deviations or conditional behavior for the Erdos-Renyi as a tool to get the typical behavior of the exponential random graph model. And in particular, the most common exponential graph model is one with one F. It's called edge and F model. It's one L. Often F is even a triangle, but not necessarily. You can take another pattern. And I just rewrote the same formula, but now simpler because I have only one function and no sum. In the dense case, this was studied. Dense case correspond to P being held fixed when n goes to infinity, like I mentioned before. And this was studied for a linear function f, which is the most natural one, just x, just count the number of triangles, or f patterns. The rate is an n square because you just have n square independent edges. And this was studied in a sequence of works, the first by Behamidi et al., and the other two came after the work of Chatterjee and Varadhan, so they could use a large deviation of Chatterjee and Varadhan in order to understand the exponential random graphs. And they discovered two problems in this situation. The first problem, it's not very interesting from an application point of view. As I mentioned, the winning strategy for the conditional measure in the dense case is a green one. It's just becoming a new Erdos-Renyi. So the typical behavior of this graph, this ensemble, is just another Erdos-Renyi with a different parameter. That's not very exciting. You didn't do all this work just to end up with something that you knew before. The second problem they discovered, there is also a degeneracy. It has to do with the way that this number grows. This is a polynomial of a certain degree. It grows too fast compared to the rate of decay of the probabilities, and as a result, in a certain range of P and beta, what you end up is that not only do you get an Erdos-Renyi, but you actually get the Q to be either 1 or 0 in a whole range of P's and betas. So you change your parameters, and you end up with either a complete graph or an empty graph. And that's not very exciting result. So this kind of gave some kind of a disincentive to use these models in an application. In this work that is currently in finishing writing with Nick Cook, we get quantitative control on the log of the partition function for P very small, going to 0. And this allows us to understand the behavior, the typical behavior of sparse Erdos-Renyi random graph. And that's what I will talk about most of this lecture. And these are predicted to have a richer structure. This was already predicted in a more vague way in a paper by Eldan and Gross from 2017. And while doing that, we also figured out a way to resolve the degeneracy. And the way to resolve the degeneracy is simply to take here, in the function here, to take the number of counts to raise it to a fractional power, and you can figure out which fractional power will give you an interesting rich behavior. So when you change parameters, you actually change the way the typical behavior of the graph holds. Yes? No, I did not say it's always. I say, well, I say it's always, but it's wrong. I should say for many choices of P and beta. It's the same regime. And in the other regime, you don't know what it is. So it's not really, okay. Okay, so let's talk a little bit about the upper tail for sparse, for subgraph counts in the sparse case. So now I move to a more general situation. I have, again, an F of maximal degree. The maximal degree of the pattern will play a role in this determining the scale. Here is a scale. I will explain to you why it comes to be that. It's n squared for the number of edges, but then as p goes down, the rare probabilities become less rare because you need to change less of the edges. And what is important here is a factor delta here, which is just a maximal degree of your pattern. So in a triangle, delta will be 2. If you take a complete graph of some other size, it will become delta or delta plus 1, depending on the size. So what we are after, we want to prove that, we call UNP delta, the minus log of the probability in the Erdos-Renyi graph of getting our rare event. And the claim is that this should be behaving like this scale times a function of order 1, JF of delta. And this function, JF of delta, should match the minus log probability of the two strategies we mentioned before, the hub or the click. You try to plant a click. You can calculate what's the size of the click you need to do in order to get the extra stuff. And you can do the same for the hub. You can calculate what it will imply as a lower bound on your tail on the probability. And one of them will be winning, depending on delta and F, one may win or the other. And the claim, the hunch, is that this is the best to do. No need to do something more complicated. And in the paper with Chatterjee, we actually got the naive mean field approximation for upper tail, which means what? We verified that this log probability can be written by a solution of a variational problem. This is the same variational problem I wrote to you with a relative entropy, product measure. Here is a basic product measure, Erdos-Renyi. The general product measure can be written by simply replacing in every edge the parameter p by a parameter x of that edge between 0 and 1. So every edge now may have a different probability. You get a new product measure, and I call it mu sub x, where x for me is simply a matrix, but with weights, continuous weights between 0 and 1. And I look at minimum of the relative entropy over all the matrices x, under which the count typically will be 1 plus delta. Here I extended the count from a count on graphs to a count on matrices with weights. What do? Whenever I meet an edge, I just multiply by the weight or the probability of being 1 instead of multiplying by 0 or 1. And I call this function phi. And what we proved is that in a certain range of p, this upper tail behave like phi, approximately. Then Bashar, Bhattacharya, Ganguly, Lubetsky, and Zhao analyzed this variational problem and proved that this variational problem scales like R and P and converges when n goes to infinity and p goes to 0 in a certain range. It converges to the number j, which matches the click or hub approximate sizes. Right? Kind of the hunch is holding in the sense that the tail probability behave like it should be. What is appearing here is that you see there is a range here for p. You cannot go too slow, but the variational problem matches the hunch in a certain range, but the first part is not getting that far. That's because of this step with the Gibbs function, which I mentioned. So the rate in which you can lower p here is very small. It's constant over, instead of being 1 over delta, it's constant over delta, but you have to divide by the number of edges of your pattern. So if your pattern is to find a click of size 10, the number of edges will be around 50. So you have a factor 50 decay, so you cannot get to where you want. And these numbers here, they were improved by Eldon, but these numbers here have nothing to do really with what you expect. You expect everything to go all the way to 1 over delta. In the two papers with Nick Cook and Yui that I mentioned here, we used a different strategy. I will explain it towards the end of the talk. We used a different strategy, avoiding the Gibbs measures, and got into first a factor 2 of the optimal, and then the optimal plus 1. So we are very close to the optimal, but still there is a little bit of gap. For special graphs, at the same time, for special graphs, O'Geary used random matrices theory to get the optimal result for cycles. If you try to look for cycles, if you calculate it in terms of the adjacency matrix, it simply corresponds to take the adjacency matrix and calculate trace of powers of the adjacency matrix. Because the cycle is I connected to J, connected to K, connected to L. You can write it as a matrix multiplication and take the trace. Now, the Erdos-Renyi random graphs correspond to matrices with IID entries. We know a lot about the spectrum of matrices of IID entries, and O'Geary was able to take advantage of it and get the optimal number. In the paper with Nick Cook, we've got another very good result for a case of a star, one vertex connected to few others. Again, it's a graph of a very nice structure, allowing us to get a much bigger number instead of factor 2 or much bigger number. The work of Harel, Mousset, and Samotic in 2019, they took the similar approach to what we took with Nick Cook, but they focused on regular graphs, graph where every vertex is connected to exactly the same number of vertices, regular patterns. Like triangle is both a cycle, a complete graph, and regular, but there are more regular graphs than cycles and complete graphs. In a case of regular graphs, there is a lot of graph theory you can use, combinatorics. They used it to modify, work closer to combinatorics, and were able to get the factor 2 over delta, which is really the best you can. In their work, there was a small gap. They couldn't handle all delta regular graph, and there was a small gap in the range of P somewhere, and Basak and Basu worked out, fixed and adapted their work, and closed the gap completely with the same approach. But the point is that also what is interesting is that this approach is different than this approach, and is different than this approach. So it was kind of different approaches to the same problem, kind of chasing the numbers down to where they should be. Okay, so in a work with Soham Bhattacharya that I'm not going to describe in detail, we ask ourselves what happened if you look beyond GNP. GNP, the Erdos-Renyi graph, is characterized by two special properties. First of all, everything is independent. That's very useful, all the edges. And secondly, everything is exchangeable. You have exactly the same P. These things are heavily used in the proofs. And we asked ourselves, can we deviate from it and still get similar results? And we took specific choices. One is when we fix a number of edges, the other one when we fix a degree, and the third one when we still keep the independence, but now we allow the probabilities to be all different, like in a stochastic block models where different groups of edges have different probabilities. And the conclusion of this work was that the first part of the naive mean field, like in the work with Nick Cook, works exactly the same. I mean, you need to modify various lemmas and technical stuff, but the principle works. You get the same results. What is very different is that the variation problem is very different. One reason it's very different, you can see already especially in the regular graph, because if the degree is fixed, you cannot do a hub. There is no way to get a vertex of degree n if the vertex is deterministically fixed to be D, if the degree is deterministic to be D. So some of the strategies cannot be worked out, so the variational problem has to be changed, and of course, an answer, the numbers also change. So in terms of the combinatorics, it changes. In terms of probabilities, there is not much change. In the paper with Yui and Nick, we also look at the case which was more relevant for us, and that is a case of making multiple constraints. And that's the same, you see the same variational problem. The only difference now you have, instead of one constraint, you have many constraints. You write, this is the naive mean field approximation. That's what we did in this paper. And in the paper we saw, we redo the work of Bhattacharya, Ganguly, Lubetsky, and Zhao, and proved that this will converge to the same principle of having a click and hub. The difference is when you have multiple constraints, you may have both click and hub, whereas when you have one constraint, you always choose only one of them. It's never beneficial to split, but when you have more than one, you may do something more complicated. Okay, so what do we learn about the conditional result? I mentioned that my goal is to understand the conditional result and not to calculate the probability of the tail. This was only means on the way to the end. And now we are getting close to the end. So again, I repeat what the story is. We have a pattern F, a graph, a finite graph, pattern, a triangle or complete graph or a star or a cycle of maximal degree delta. And we are interested in this rare event where the count, the normalized count of the number of these patterns exceeds the nominal value 1 by a factor delta, by an additional delta. And we are interested in the conditional law of our Erdos-Renyi graph given the conditioning. And our conjecture or our prediction is that in the domain where the solution given by Ganguly and by Bhattacharya, BGLZ, is to say that it's either a clique or a hub, the answer for the conditional will be exactly that. You take the Erdos-Renyi graph and you plant a clique or a hub of a suitable size, and you determine the size by what you need to get this excess. Right? So this is a conjecture, and we are trying to get to this conjecture. So let me show you a picture of this conjecture, right? So you start with an Erdos-Renyi random graph, and imagine that the Erdos-Renyi random graph is like a picture in the Louvre, but you look at it from far away, from maybe the next room. So it looks to you, even though it's full of zeros and one, it looks to you like a certain kind of grayish P density of the edges. If you are the green strategy correspond to looking from far away to simply changing the gray level to a darker one. The planted clique and hub correspond to finding somewhere, if especially you need maybe to rearrange the vertices in a certain order, but finding there a nice blocks full of ones, dark, complete dark, black. The hub strategy correspond to this box, right? And if you want to understand where the scaling comes from, it's very simple. If you want, for example, here to produce the right number of excess things, you will need to put here n, little n times p to the delta over 2 times little n times p to the delta over 2 times a constant. Total number of ones you will need to put in will be n squared p to the delta. The probability of changing from p to 1 is p. So now you raise p to the power constant times n squared p to the delta, and you write it as e to the minus constant times r, and you recover this number r. That's the r that appeared in the original slide. That's how it comes to be. Okay, so we are after this situation. So what was done already? In the paper of Harel et company, they looked at the complete graph. And for the complete graphs, for collecting complete graph, because complete graph is very easy, they were able to prove not only to get the upper tail probability, but to verify a piece of this conjecture. They were able to show that in a domain of P's where they can work, with high probability, conditioned on this event for the complete graph, the graph contained almost a clique or almost a hub of the correct size, of this size that I mentioned that needed to be. So in principle, what they proved the existence of the black pattern. They did not prove that the piece on the side remains unchanged, but they proved that there exists this approximate black pattern. In this paper, in writing with Nick Cook, we verified that the same applies for any F, for any pattern, in a domain, again, in the domain that is determined by the domain in which we can do the first part. And we get a stronger statement of the above conjecture if we take a different domain with a slightly, like the domain that we had in our first paper. And what is the difference between this and that? Is that in the conjecture, we verify not only that we have the black, but also that the part with the P remains unchanged, approximately. So you actually have most of the graph is unchanged, and you planted something small. So this is what we can prove. Okay, so what is this? What is a conclusion about the typical structure of the Erdos-Renyi exponential random graph model? So in this story of the exponential random graph model, I remind you, I have a collection of patterns, F, vector. I have a collection of parameters, delta, vector. I have a parameter, beta, positive. then the variational problem that I mentioned, I didn't try to use the variational problem, but this variational problem has a certain set of optimizers, and the set of optimizers, the choices of the optimizer in this variational problem is a finite. This we can prove. There is only finitely many optimizers. Many times it's only one, sometimes it's not more than one. And under suitable conditions, this is why the question mark, this is not general, but under suitable condition, the set of optimizer for the variational problem associated with the Erdos-Renyi, with the exponential random graph model, the one which determines the log of the partition function, is also finite. This requires some extra condition, but let's assume that we put these extra conditions. So we have a finite set of optimizer for both variational problems. What can we say then? Then what we can say is the following theorem. If you are in the domain of P that I mentioned, then with high probability conditioned on the rare event, you will find yourself a clique of appropriate size and a hub of appropriate size. This is what I wrote here, the set of vertices I and I prime, such that if you look at the graph restricted to I, you will find approximately a clique. What does it mean? That every vertex will have a degree in that graph, almost a complete, meaning 1 minus epsilon, the maximal degree in that graph. And in the red part, in the hub, what you will find, that you will find most of the vertices in this second group will have degree almost n, 1 minus epsilon n. Epsilon is a parameter of tolerance. That's what I mean by almost a clique and a hub. And if you take the more restrictive domain, you actually know more. You know that your adjacency matrix, if you subtract from it the version, what I call a clique and hub matrix, that is a matrix which is, like I showed you, it's one, black one where the clique, a black one where the hub, and everything else is P. And you look at the difference between these two matrices, the spectral norm, the maximal eigenvalue of this matrix, is relatively small. Relatively small here means smaller than n times, much smaller than n times P to the delta over 2. So it's a stronger statement about it's not just the appearance of the black part, but it's also the distance from something which is otherwise P is very small. If you look at the exponential random graph model, what you do, you change, instead of taking your two parameters of the optimization, the size of these sets from one set of optimizers, you take it from the other set of optimizer corresponding to the tilt, and otherwise it's the same story, and now it's a typical behavior under the Gibbs measure instead of being conditional. Exactly telling you is mathematically what I told you informally in the beginning of the lecture. So this was verified in this domain, in this paper that is, was supposed to be on archive already, but will be on archive soon, maybe a few weeks. Okay, the proof of this, result hinges really, okay, the proof of this result hinges on crucially using stability for the variational problem. So what's the issue here is not the probability, but the issue is analysis. You already got yourself a variational problem. You found a bound on it that matches the best strategy, but it doesn't prevent other things to fight and be also possible. So what you need to show is that in this variational problem, whenever you try to deviate from the optimal strategy, you actually get a positive raise in the value, or the probability will actually, the exponential decay in the probability will be much smaller, so you can neglect all this. So it's a lot of analysis, especially we need to do there is an inequality called Finner, generalized Holder inequality, and we need to study cases of equality in that inequality and do quantitative analysis of various combinatorial structures. So most of this paper is really analysis, not probability. Okay, let me, in the remaining very short time, try very quickly to go over the principle of the proof of the first part. So first I'll start with a summary of what is done in Chatterjee and Varadhan. So Chatterjee and Varadhan do a classical large deviation. What is a classical large deviation principle? You try to calculate that minus log probability of E, a set, nice set E, is Rn times the infimum of a certain variational problem for all the sets E, or many nice sets E, in a common space X. The importance here is a common space X. Now, in our case, the graphs are not in a common space. When you change n, the graph go to a different place. So what you need to do, you first need to identify the set of graphs via their adjacency matrices with one common space. And the way you do it via what is called graphon. What you do, you take your graph and you look at the ij entry of the graph and you put it in position I over n times j over n, make a little box and color it with 1 or 0, and this gives you a piecewise constant function on 0, 1 square. This is a subset of the set of all possible symmetric functions, measurable symmetric functions from 0, 1 square to 0, which 0, 1, which you call W, the space of graphon. This is like a continuum adjacency matrix. You kind of forget the discreteness of the adjacency matrices. And on this space, you need to put some topology. And to put some topology, you need to put a distance or a metric. And the metric that people put there is a cut norm metric, which is given by this formula, which is a generalization of the cut norm matrix, norm for a matrix. For a matrix, a cut norm, the cut norm is to take the matrix M, choose two subsets of rows and columns, sum all the entries of the matrix in these rows and columns, takes the absolute value, takes the maximum of all the choices of the rows and columns. If the matrix is positive, this is trivial. You just end up with a sum of all the entries of the matrix. If the matrix is changing signs, it's not always best to take all of them. And this is analogous to the picture I showed you before of looking at the matrix from far away. That's exactly this graphon business. You make every dot, every box very small, and you just look at the average behavior. Okay, so why this is working? This is working because this space of graphon is really a topological reformulation of something called regularity method from extremal graph theory. Regularity method correspond to something well known called Semeradi regularity lemma, which I will not explain, but roughly speaking, saying that whenever you take a graph, you can eliminate a small number, relatively small number of vertices, and whatever is left, you can break into not too many groups. And then the density within group A to group B, density of edges, will be typically very few fluctuation, kind of almost constant in a certain relaxed way. So Semeradi regularity lemma, when you translate it into this framework, really tells you that after you do a vertex relabeling, because you don't really care what the order of the vertices is, that is like a quotient in the space of graphons, it makes the space compact. Now, compact is very good for large deviations. Even people who don't know large deviations should remember compact and large deviation like each other. And in particular, this was the key to the proof of Chatterjee and Varadhan of the large deviation. What was needed was exactly compactness. Compactness came from a regularity lemma. But you need one more thing. You want, at the end, also to conclude that what you learned, the large deviation that you produced, has relevance to the functional that you are trying to study. In this particular case, it's this count of the subgraph count. Subgraph count have the property, this is called the counting lemma, that they are continuous function on the space of graphon. This is actually the space that makes all of them continuous and doesn't make anything else continuous. That's one way to define it as well. So since they are continuous, you can apply your large deviation. Large deviation applied to continuous function. That's similar to a weak convergence applied to continuous mapping. And you can get yourself the upper tail of this. So these two facts are really the key to the paper of Chatterjee and Varadhan. So you want to do the same, exactly the same maybe, in the context of sparse graphs. The moral here is that, as I said, the cut norm topology, the one that comes from this box distance, is optimal, perfect for dense graphs. You want to do it for sparse graphs, and you encounter a problem. And the problem you encounter is that the regularity and counting lemmas are not accurate enough to capture anything that is relevant for sparse graphs. The problem is that we make changes on a very small part of the graph. And the change in a very small part of the graph is all that you care about. And the whole point in the regularity and counting lemma is to look at things only at the level of n vertices. Never look at pieces of groups of vertices which are much smaller than n. So it's completely impossible to do it. And not only that, people in combinatorics were looking for extensions and refinement of regularity and counting lemma, and they even proved that this cannot be done. So there are examples that show that what you need to do in order to achieve this framework for a sparse graph is simply impossible to do this way. But if you remember, we already have the lower bound on the large deviation for free because we know what the answer should be. So we only need to do the upper bound. The upper bound amounts to essentially covering the space efficiently. We want to take many small sets on which our functional does not change too much, and to cover the space with these sets, and we have a union bound. We don't want the union bound to cost us too much. So a very good tool here is the following fact, which is known in large deviation, that whenever you take a convex set, you get automatically an upper bound, which is perfect. There is no cost, just e to the minus r times the function. This is a result coming from the min-max theorem. It appears in exercise in many textbooks, and I know where it is in the textbook I wrote with Ofer Zeytouni. So what it means is that it suffices now to cover the space of all possible graphs, embed it in this space which is becoming a vector space. So you can talk about convex sets, a space of where you change the 0, 1, the discrete, to an interval 0, 1, and you want to cover it by not too many convex sets. Not too many convex sets, that means less an exponential little order of the rate. So the union bound will not change, they don't have an effect on the probabilities. And you want to be in such a situation that these sets are small enough that the function that you are interested in is not varying too much over one particular set. So if you take the function, you can say, in this set, the function has a certain value. So either the whole set belongs to my rare event, or the whole set does not belong to the rare event. And this is exactly quantitative compactness, this efficient covering, and quantitative counting lemma, this efficient control. You will not be able to do it, because if you can do what I just said here, you can do an improvement to what I said you cannot do as a conclusion. But what you can do is you can do everything if you exclude a set whose probability under Erdos-Renyi graph is so negligible it will not affect your answer even at a large deviation scale. So this makes it into a probability statement, this piece. Otherwise, it's just a statement about analysis and combinatorics of graphs. And that's the approach we took in these two papers. And in the first paper, we use a spectral theory. In the second paper, we use a cut norm. So let me tell you what it is, a spectral theory. So you fix some parameters here. Delta prime, epsilon should be small, L and L, K should be large. And then if you are in a certain range of N and P, you can cover the space by one negligible set and many, but not too many, small spectral balls of this diameter. And the second part, the counting part, says that if you have a set of some certain diameter, which has a certain property that it's not, the count is not large on all the points, and this property is again, violating this is a negligible set, then the control, the functional that we are interested in is not changing too much in this set. So in order to make this work, what you need to make this number here, delta star, equal to delta prime over 2, that is take delta prime equal to 2 delta star, and then the whole scheme will work for you. Modulus and negligible sets. Now we work here with spectral regularity because spectral sets correspond to eigenvalues of random matrices for which we have a nice theory. In the second paper with Yui, we wanted to work on tensors, on hypergraphs. There is no spectrum there. So we changed to a cut norm. We moved back to the cut norm, but we normalize the cut norm by a weight which depend cutoff scale because we didn't want to make very small sets influence what we are doing. And we got exactly the same results, more or less, but now the diameter is measured in a different way, and the parameter is now delta plus 1 instead of being 2 delta. Thank you very much. And happy birthday to them.
Thanks. Thank you very much. Other questions?
Thanks a lot. So you mentioned at some point that this was working if you want to increase the density of triangle, and this is very much more complicated if you want to decrease. So I could not see why, because the large deviation principle of Chatterjee and Varadhan works, right? If you want to do large deviation, you know, on the left. And then it's to solve the variational problem that is difficult.
In the dense case, it doesn't matter. It's the variational problem is very difficult to solve. There was a reason why I drew only half, because I don't know, the solution on the other half is very complicated. In the sparse case, you cannot even get the other half. Or you can get the other half, but it's much less satisfactory results. The idea here is the following. Think of what we did correspond to ferromagnetic models. In ferromagnetic models, everybody tried to align the same way. Usually, it's really easy to decide what is the best strategy. In anti-ferromagnetic models, it's harder. And especially here, what you see, for example, if you want to violate triangles, you don't want to go to the empty graph, that's too costly, but what you can do instead, go to a bipartite graph. In a bipartite graph, there will be no triangle. So you try to eliminate edges, but you try to eliminate edges in a clever way, and this clever way is global. It involves the whole graph. It's not local like what I did here. So it's more complicated. The variational problem is more complicated. There are results, but they are much more partial. So that's why I didn't go over them.
Okay. Other questions in the room?
Okay, thank you, Amir. You mentioned at some point that I think it was a joint work with Bhattacharya that your result extends to a random d-irregular graph. And I was wondering whether you could more generally also deal with graph where the degree sequence is given and with view towards the random configuration model.
The case where the degree sequence is given, we did not do, but you could do the case where there are finitely many choices for the degrees. That is kind of the same principle, it's just more work. If every vertex has a different degree, it's get hairy because you can approximate, but it's getting harder. It looks more like the inhomogeneous part. But what I must warn here is that the part of solving the variational problem gets very complicated once you have more choices for the degrees. The part of the probability is kind of goes through relatively easily. It's a variational problem which gets harder because you have these constraints. So what you wanted to do is now not possible to do.
Okay, other questions? I think there is a question in the chat.
Yes, I was
turn on your mic.
I was just wondering, do you hear me?
No, we can't hear you. You have to unmute yourself.
Yes, but I unmuted me.
We can hear you, so it is a problem in the room.
Okay.
You see where to do it? It should be on the lower left.
Oh, maybe we can. You can ask the question for me. It was
on Zoom. You can hear.
It's on the chat.
Wait a second. Can you try?
Yes. Do you hear me?
Yeah. Now, yes.
Okay. Yeah. I was just. I had just a question. If people in applied math use these exponential random graph models, I was wondering how do they simulate them? How do they sample them? Is it easy? Did you?
The answer is directly to simulate them is hard because of the partition function, right? Because there's a problem with these Gibbs measures on discrete models. It's hard because of the partition function. That is hard to calculate. There is no formula, exact formula for it. Otherwise, we didn't need to do the estimation. But you can use Markov chain Monte Carlo ideas to get to run a simulation that will converge fast and with equilibrium with that. Because when that's a general strategy for Gibbs measures with complicated partition function. You just when you make a Markov chain Monte Carlo, you can just deal with the ratio of the two probabilities when you make the changes, and if you adjust them correctly, your Markov chain will have an equilibrium measure, which is a Gibbs measure. So you can just run it for a long enough time, and then that will get a sample. So that's typically the way they sample from these distributions.
But do we have any guarantee that the mixing time is low enough? Is here
in the paper, in the dense case, this was done in some of the in the sparse case. I don't know for work doing that, but in the dense case, this was done in some of the papers I mentioned. They were actually looking at the mixing time, and the mixing time should be definitely mixing time should be nice if the answer is Erdős-Renyi. It should not. The mixing time is usually difficult when the answer is complicated. How it looks typically. If it looks typically not very complicated, the mixing time should not be hard. In the sparse, I think the mixing time might take longer, depending on how sparse it is, because the planted pattern is small. So somehow I think it might be more difficult. But in general, these are not the worst things to simulate because they are not disordered. They are ferromagnetic. So I would imagine that it's not so bad if beta is positive.
Thank you.
Okay. If no other questions, then let's thank the speaker again. Okay.